This is a lesson on light. Light is a form of electromagnetic radiation. If you disturb an electric field or a magnetic field, you will create light or at least electromagnetic radiation. Light is a pure energy. Light has many different forms. Technically, electromagnetic spectrum does. Electromagnetic spectrum. If I remember these from middle school. At one end you have radio waves, and next to them are microwaves. Next to them are infrared, IR, which is heat. Then there's a thin little thing of visible light, not very much of the spectrum. Invisible light made up of Roy, G, Viv, red, orange, yellow, green, blue, indigo, violet. And beyond violet is ultraviolet, stuff that gives you skin cancer. And then X-rays and gamma rays. So this is the electromagnetic spectrum. You have to know this. Characteristics of light. Light or waves of any sort. One is wavelength. Wavelength is the distance from one portion of a wave to an identical portion of the wave. Its symbol is the Greek letter lambda, which is L, and it's the length from one part from one corresponding part of the wave to another, and it's measured in meters. A diagram, this would be one wavelength right there. You don't have to go like that. You don't have to measure it from where it crosses the axis to the axis. This would not be. This is a half wavelength because this is crossing the axis going up. This is crossing the axis going up. So that's corresponding. You could draw a series of waves, and that would be a wavelength from the top to the top. That'd be a wave from bottom to bottom. You could go 2/3 up, 2/3 going up. So that would be one wavelength. So all of these are wavelengths. And again, they must be in meters. Another characteristic of wave is frequency. Frequency is abbreviated with the Greek letter nu. Some textbooks use F. Fortunately, we're doing nu, which the Greek letter N stands for number of waves per second. And it is abbreviated Hertz. Gigahertz, cell phones, computers, something like that. That's how many frequency that they can perform functions on. Another characteristic of all waves is speed. And if you're talking about electromagnetic radiation, all of the radio gamma rays travel at the speed of light. Which in a vacuum is 3 × 10⁸ meters per second. So that is speed in the The fourth characteristic of light is amplitude. Amplitude is the height of the distance of the disturbance. It corresponds to loudness for sound, brightness for light. There's just more of the stuff coming at you. Up here, the electromagnetic spectrum, radio waves have the longest wavelength. That means gamma rays have the shortest wavelength. Radio waves have a smallest frequency, shortest frequency, or lowest frequency. That means gamma rays have the highest frequency. These are inversely proportional, which means the speed of light, 3 times 10 to the negative 8, is equal to lambda nu. So if you know one of the two, you get the other one. Say the wavelength is 3 times 10 to the third. And if you plug that in to the formula, 3 times 10 to the 8th equals 3 times 10 to the third times frequency, divide 3 times 10 to the third, get 1 times 10 to the 5th hertz as your frequency. Energy and matter. Energy and how it reacts to matter. Energy is not continuous. It looks like it might be. It looks like you can smoothly go from one microwave to another microwave with higher things. But we find out that it is, in fact, quantized, which means it is chunky. It comes in discrete units. Just like the Greeks thought that matter was continuous, and then we found atoms, which are quantized, smallest bits of matter. So that we call these chunks or particles or packets of energy photons. There's an equation for energy. Energy is equal to something called Planck's constant times frequency, where Planck's constant is 6.63 times 10 to the negative 34th, and which is very, very small. So that's why you don't notice chunks of energy coming by you. Energy looks smooth, but when you quantize it, you take a very small segment and expand it out, you find out that there are steps. And each step has a length or a height of 6.63 times 10 to the negative 34, which is an incredibly small number. So you can be on this level, you can be on this level, but you cannot be in between. Using this example up here, we now have the frequency. So E equals 6.63 times 10 to the negative 34th times 1 times 10 to the 5th. Do the math, you get 6.63 times 10 to the negative 29 joules unit of energy. Einstein used this concept of matter and energy and this equation to come up with an explanation for the photoelectric effect. The photoelectric effect is essentially what makes your solar-powered calculator work. What happens is, if you shine light on some piece of the metal, it will absorb that energy and produce electricity. Well, if you don't have enough energy, you cannot do that. So this is what Einstein won his Nobel Prize for. The theory of relativity was too controversial. He said that if light was a wave, all that energy is spread out across the entire surface. Well, that doesn't work because that average energy does not give you enough energy to kick out any electrons to produce electricity. So it doesn't do that. But if he said that light were photons, or chunks of matter, concentrated, so all the energy of this wave right here is concentrated in that one, and all this energy here is concentrated in that one. So they come in and they zap an electron, and yes, electrons can work. Now the problem with this is not all types of light will produce electricity. You can shine red light on a solar cell for a long time, and absolutely nothing's going to happen. What you need is violet light or ultraviolet light. Violet light alone has enough energy to remove electrons and make the photoelectric effect work. And that's coming from E equals Planck's constant times nu. The amount of energy depends upon the frequency. The higher the frequency, the more energy. There's a cutoff point about green light or indigo light. Indigo light, there's a cutoff out. Anything with that frequency does not have enough energy to get the electron kicked out. So he won the Nobel Prize for doing that. Red light just doesn't have enough punch in its photon to kick out the light, kick out the energy. That concludes this lesson on light.